Hello and welcome. As usual, it is your teacher, Mr. Chocha, and today our topic is heat transfer. Our specific objectives are, by the end of this topic, the learner should be able to state the difference between temperature and heat, state and explain the modes of heat transfer, describe experiment to illustrate factors affecting heat transfer, explain applications of heat transfer. Once again, welcome. Let's move together. A common question in this topic is, state three differences between heat and temperature. Alright, temperature is the degree of hotness or coldness of a body on a chosen scale. Temperature is the degree of hotness or coldness of a body on some scale, while heat is a form of energy that flows due to temperature difference. So while heat is a form of energy, temperature is the degree of hotness or coldness. The second difference lies in the unit. Temperature is measured in Kelvin, while heat is measured in joules. Anytime you're writing Kelvin in words, write K starting with small letter, but if it is symbol, then it is capital K. The same applies to joules. If you're writing it in words, let it be in small letter. J should be in small letter. But if it is symbol, let it be capital J. Finally, there is an instrument that is used to measure temperature, and that is a thermometer. However, there is no known instrument that you can use to measure heat directly. Thank you. Let's move to the next slide. Modes of heat transfer. Modes of heat transfer. Ways in which you can transfer heat from one point to another. There are three modes of heat transfer. I hope that by now you're familiar with them. The first one is conduction, then convection, and finally radiation. There are three ways in which heat can move from one point to another. That is conduction, convection, and radiation. Can you be able to identify these three modes of heat transfer on the diagram? If yes, that's good. Let's move on. I know that in primary you learnt that conduction is the mode of heat transfer in solids. However, that is a wrong definition when it is in secondary level. In secondary level, we define conduction as a mode of heat transfer by vibration of particles. A mode of heat transfer by vibration of particles or movement of free electrons. I'm repeating this. It is a mode of heat transfer by vibration of particles or through movement of free electrons. Of course, there are very many variations of defining conduction. As you can see from my definition there, conduction is the transfer of heat from particle to particle of an object without the movement of the object as a whole. The key point is that in conduction, it is the particles that vibrate, transferring energy to the other particles which also vibrate, transferring energy to the next particle which also vibrate. But remember, even though the particles are vibrating, the object itself does not move. So mechanism under which heat is conducted is by vibration of particles or molecules and through free electrons. We can classify materials as good conductors or poor conductors depending on how they conduct heat. If they use both vibration of molecules and free electrons, then they are classified as good conductors. A good example is metals. However, if they only conduct by vibration of particles, then they are poor conductors. Let's move to the next slide and see what is there. Examples of good conductors. All metals are good conductors. Copper, tin, silver, lead, aluminium, zinc, brass, iron, mercury. All are good conductor of heat. And I told you, if you want to know whether a substance is a good conductor of heat, then it conducts heat by two methods. One, by vibration of particles, and two, by movement of free electrons. Are you familiar with that by now? If yes, thank you. Poor conductors. Another name used for poor conductors is insulators. These are material which do not readily allow heat to pass through them. Air, water, rubber, plastic, glass, asbestos, concrete. These are poor conductors of heat. This experiment shows the difference between a good conductor and an insulator. A good conductor will always conduct heat away, but an insulator does not. Now take an example of this. If you have if you have a metal and wood, then you can wrap them together using a piece of paper. Then if you pass flame over the piece of paper, you realize that the paper will be charred or burnt at the end where wood is. But at the end where copper is, the paper will not be burnt. Reason. This is because wood does not conduct heat away, so the heat concentrates and burns the paper. However, copper conducts heat away, and therefore it doesn't concentrate on the piece of paper to burn it. Have you understood? Thank you. The aim of that experiment was to determine between wood and copper which one is a good conductor and which one is an insulator. From the above experiment, we can say wood is a poor conductor of heat, and that's why it did not conduct heat away, making the paper to be burnt. However, on the other hand, copper is a good conductor of heat and conducts heat away from the paper, and that's why the paper did not burn. You can try this experiment at home. Thermal conductivity. Thermal conductivity is the ability of a material to transfer heat. Some materials are better thermal conductors than the others. I want to say thermal conductivity will tell you how fast a material conducts heat. Factors affecting the rate of thermal conductivity. How fast a material conducts heat depends on 1. The nature of material. There are some materials that conduct heat faster than others. Second is the temperature difference. Third, the length of the conductor. And last, the cross-sectional area. So, 4 factors affect rate of heat transfer. Nature of material, temperature difference, length of the conductor, and very good. We are going to look at these factors that affect thermal conductivity one by one. So let's start with nature of material. So as we've said, some materials are better conductors than the other. So look at this. We have brass, iron, we have copper and aluminum. There is some pin attached to these metals using some wax, and also you can be able to see that these metals have been connected to a water bath which is hot. So the water bath will burn the metals, and heat will be transferred to the wax, making the wax to melt, and then the pins will fall. So which pin will fall first? Copper will fall first, followed by others. Reason: copper is a better conductor than the other. Let's see the order in which this wax will fall. Pin attached to copper drop first, followed by that of aluminum, then brass, and then iron. Conclusion: some materials are better conductor of heat than others. However, for this experiment to be successful, then you must take the following precautions. 1. The rods must have the same diameter. 2. Rods must be of equal length. 3. The wax must be of equal size. 4. Similar pins to be used. And finally, same source of heat. And the water bath is more excellent because it provides uniform heat to the rods. Unlike just burning the rod directly using a flame, you will not be able to provide uniform heat. Santi. To the second factor that affects rate of heat transfer, and that's the length of the conductor. The shorter the length, the faster the heat is transferred. I think this is logical. So thermal conductivity is inversely proportional to length. What this statement means is that if thermal conductivity is to be high, then the length has to be short, and vice versa. The shorter the material, the higher the amount of heat transferred. So if you do an experiment as illustrated in the diagram, you realize that the pin very near to the burner or flame will fall first because heat will reach it first, and then followed by the pin which is next to it. The pin which is farthest will fall last because it takes time for heat to transfer from one end to another end of a long conductor. The experiment is almost the same as the previous one. These are thermometers. As you can see, the thermometer near the flame is showing high temperature, while the thermometer farthest from the flame is showing least temperature reading. This shows that as heat moves away from the source, it keeps on reducing. It is observed that the pin near the source of heat falls first, while the pin farthest from the source falls last. Explanation: the large amount of heat reaches the first pin. As length increases, heat reduces because some of it is lost to the surrounding. The path followed by heat is called line of heat flow. Lines of heat flow diverge as they move away from the source, and once they reach the surface, heat is lost to the surrounding. You can see the diagram illustrating this in the next episode. In a line of flow, they transport heat from one point to another. As you can see, most of them are being lost on the surface near the source of heat, but as you move away from the source of heat, fewer and fewer line of flow reach that end. This shows that as heat moves away from the source, it keeps on reducing. So since temperature can be used to show amount of heat, from this graph you can see that temperature keeps on reducing as length increases. So as you move away from the heat, temperature keeps on reducing. As you move away from the source of heat, temperature keeps on reducing. That is for a material which is not lagged. What is lagging? Lagging is covering a conductor with an insulator. Why? To prevent heat loss to the surrounding. If you lag, the line of heat flow will not diverge outside, but will move parallel to each other. Can you see the slide? That's a bit better. So as you can see, lagging is the covering of a conductor with an insulator to minimize heat loss to the surrounding. Lagging make lines of heat straight. Look at the diagram. They are no longer diverging outwards, but they are moving outward, straight forward. So because of this, minimum heat is lost. And you can now see if they ask to draw a graph, the graph does not drop abruptly. Instead, it falls very slowly and by a small margin, showing you that a very little amount of heat is lost when you lag a material. I believe that you've seen lagging even in electricity wires. Maybe you are sitting next to a TV. That cable that takes current to the TV, you can see it has some plastic covering on it. That is lagging. Also electrical wire taking current to the bulbs also are lagged to prevent heat loss to the surrounding. The diagram shows two graphs, one for a lagged material and another one for unlagged material. As you can see, the one that is not lagged, a lot of heat is lost and the temperature falls very, very fast. But the one that is lagged, yes, heat is lost, but not as much as compared to the one that is not lagged. This application is made in iron pipes carrying steam from boilers. They are covered with thick asbestos material, which is an insulator to reduce heat loss from steam. The third factor that affects rate of heat transfer is the temperature difference. The larger the temperature difference, the faster the heat is transferred. Look at the setup. If you have water which is at 90 and another one at 50, then you connect the two using a rod with the wax at the middle, and then you make another setup with the water at 90, another one with at 20, and you connect them again with the same rod with the wax at the middle. You realize that in the second scenario, where the temperature difference is big, wax will fall fast. Reason: when the temperature difference is big, heat is transferred very fast. If you have a piece of metal, you put it on a candle, it will take a long time for heat to reach your hand. However, if you put that piece of metal in logs of fire, you realize that heat will reach your hand very fast, because logs of fire have a lot of heat temperature. So the temperature difference between that end, which there is heat, and where your hand is very big compared to temperature difference between the candle and your hand. The last factor that affects heat transfer is cross-sectional area. The bigger the cross-sectional area, the faster the heat is transferred. Do you know that a thin wire transfers heat slowly compared to a thick wire? The reason why a thick wire transfers heat faster is because it has very many atoms that can vibrate and transfer heat. Another way of saying this is that a thick wire has many electrons, free electrons, that can transfer heat from one point to another. So these are common misconceptions where people think that a thin wire is a better conductor than a thick rod. But right now you know. experiment above to succeed, then you must have heat the metal at equal interval of time. You must use equal length of rods, same size of wax, and rod must be placed equidistant from the source of heat. Did you know that also liquid can conduct? The only problem is that they are poor conductors. There is a difference between poor conductivity and not conducting. Yes, liquids conduct, but conduct poorly. They conduct poorly. So let's do an experiment to show that liquids are poor conductors. All you need is a boiling tube, a heater, some water in the boiling tube, a wire gauze wrapped on ice, and you're set to go. So if you set the experiment as shown in the diagram, if you heat the water to the top, the water will boil, but the ice at the bottom will not be able to melt for a long period of time. I'm not saying that now if you heat it the whole day it will not melt. No, for that short time that you're heating, let's say the water starts boiling at the top, the ice will still be unmelted at the same time. This is because water is a poor conductor. It does not conduct heat downwards. So water is put in a test tube, ice wrapped in a wire gauze and dropped in the water. The water is heated at the top. It was observed that water at the top boils, yet ice does not melt. This is because both water and the glass are poor conductor of heat. Mind you, the ice was wrapped in wire gauze so that it does not float. If you leave ice alone without wrapping it on the wire gauze, it floats on water. So we wanted it to sink down. 2, we are heating water at the top because there is no way that water will send heat by convection downwards. Convection always moves heat upwards. So we are eliminating heat transfer by convection. So this is a demonstration showing you that water is a poor conductor, because if it were a good conductor, then it will have conducted heat downwards and made the ice to melt. We mentioned that liquids are poor conductors. However, there are some liquids that are better conductors than the other. A good example is mercury. Mercury is a better conductor than water. If you set up an experiment as shown in the diagram, attach wax at the bottom of the containers, one having mercury, another one having water, and then connect a thick copper rod to both tubes and start heating at the middle. You realize that wax on mercury will fall at an earlier stage. Reason: mercury is a better conductor than water. Gases are even worse conductors of heat. The reason why gases are bad conductors of heat is because they have very large intermolecular distances and have no free electrons. Conduction in gases can be demonstrated using the experiment below. You need to light a Bunsen burner and then bring close a matchstick, but not touching the flame. You realize that the matchstick does not burn. This is because the air between them is a poor conductor. We are almost there to the end of this lesson today, and I want us to look at some of the applications of conduction. Home electrical appliances, frying pans, electric kettles, iron box. Their handles are made up of poor conductors or insulators, so that to protect the user from being burnt. Another good application of conduction is in soldering iron. Have you ever seen those people call fundis of radios and TVs using a certain metal to burn other metal? That metal is called soldering iron. So iron rod is a good conductor of heat with copper tip. The handle is made of plastic, which is a good insulator. Application of heat transfer we've already mentioned, but these are still other applications. Cooking utensils, e.g. saucepans, frying pans, boilers, base of electric irons. These are made up of good conductors, so that they can receive heat very fast. Have you ever seen birds after rain? You realize that their feathers are somehow risen. Why do you think that birds raise their feather when it's so cold? This is because they need to trap air. Did you know that air is a poor conductor of heat? So once they raise their feather, they trap air, and air insulates their body against heat loss. Again, birds raise their feather to trap air, and since air is a poor conductor of heat, it insulates the birds, minimizing heat loss from their body. Now you know. Finally, I want to also talk about heat sinks. You will find them in almost every electronic equipment, for example, computer. Mostly they are made up of aluminum. You will find them very shiny, and the reason why they are made up of aluminum is because it's a good conductor, and it prevents heating or overheating of computer. So they conduct heat away from the computer or from the radio or from any electronic component. You can see that large picture that you're seeing at the middle, shiny one. That is a heat sink. So finally, the true finally, I want to say that in tropical regions, houses are built with two walls, and some insulator is put in between the walls, e.g. glass fiber or fiberglass, to minimize heat loss to the surrounding. This also is applied in cold regions. You don't want a house to lose heat to the surroundings. So what do? You build two walls, and in between the walls you create or you insert fiberglass. This fiberglass is a poor conductor of heat, so it will not enable the house to lose heat to the surrounding. I'm very take it for granted that you've stayed with me from the start up to this end. Thank you so much, and I am asking you to subscribe and also refer your friends and relatives who want to learn physics to this channel. I want to say firefighters usually wear suits made up of asbestos. This is because asbestos is a poor conductor of heat, and it therefore protects them from being burnt. Thank you so much for being with me up to this end. I hope that you're going to come back so that we look at convection and radiation. Asanteni sana.